All right, this is the Geometry Unit 7 Lesson 3 video. Continuing to kind of explore circles and the different kind of aspects of them and different ways that we look at them and the different kind of parts. And so this one is going to be all about what we call arcs and chords. And so I'm just going to walk through some of the terminology to begin. So the first thing you got to understand is that we look at a circle. We have our center here, so this would be called circle X. That's what that refers to, the center there. And so we look at a circle. Any angle that is in the circle, like this, for instance, that contains the center as one of its points. I'm going to go ahead and mark a couple points here. We'll call this point A, call this point B over here. Any angle that's made up of these kinds of points, so 2 points on the outside of the circle and the center of the circle, is called a central angle. So the angle AXB that we see here is a central angle. So a central angle is any angle that has the center as the vertex. Center is the vertex. So when we do this, we end up with the central angle like we've already talked about, and we end up with this part right here. This part of the circle that I'm going to go and grab and draw on the line. But that highlighted portion of the circle is what we call an arc. So this is an arc. So an arc in a circle is the curved path between any 2 points on the outside of the circle. So here we would have what we call arc AB. So arc AB is the arc made up of the angle AXB and the curved path around the circle from A to B. Okay, so AB, or arc AB, and you can see the way the notation is written right there, arc AB is what we call a minor arc. So a minor arc is the arc that takes the shortest path from those points to each other. So to get from A to B, the shortest path around the circle is the highlighted portion that you see here. That is what we call a minor arc. Now, we also might have another point on the circle, let's say over here. And we'll call this point D. And if I wanted to talk about the other part of this circle, the other path, let's say the path I'm going to highlight in blue, that would be the path that goes all the way around the circle through point D and to point B. So that we would call arc ADB. So ADB is what we call a major arc. So the differences I want you to notice is that a minor arc is the arc that is inside the central angle. It's the shortest path. So we can see the direct connection between AXB, this angle that we've drawn at the beginning, and the arc AB. It's the shortest distance. So we have angle AXB, and then we have the arc AB that we've drawn here in yellow. And then the longer path that goes around the circle would be called ADB. And notice there's an additional letter here to indicate that it is the longer arc. So I only need 2 letters when I'm naming a minor arc, but I need 3 letters when I'm naming a major arc. So let me draw a couple more examples of these just to kind of drive the point home. So let's say I have some circles. I'm just going to do a bit of a summary here of what I just got done talking about. Call this point M, call this point O, call this point N. We'll do the same deal over here. M, O, N, and I'm going to add another point called point P right there. And then over here, I'm going to draw another thing. So there's another term we haven't talked about yet. Okay, so these are the three main types of arcs that you have when you're dealing with circles. The first, we already discussed, but is the minor arc. This would be a minor arc called arc MN. The thing you need to know about minor arcs is that they have a measure that is less than 180 degrees. And we'll talk more about that in a second. Major arcs go the long path around the circle. And this would be arc MPN. And this has a measure that is greater than 180 degrees. And then lastly, you have semicircles, which I haven't discussed yet, but go ahead and introduce that now. Semicircles has also three letters in its name, X, T, Y, and they equal 180 degrees. So I've kind of introduced a new concept, but I want to kind of make sure that we understand that in a circle, I think you already know this from some previous units, in a circle, circles have 360 degrees that make them up. And what I mean by that is if I have a circle, I can imagine that there's 360 little slices of the circle. This is called 1 degree. 1 degree. I think we covered this in a previous lesson, but I just wanted to make sure you understood that. So when I say that the minor arc here is less than 180, all minor arcs are less than 180 because they're always going to be, again, made up of a central angle, and that central angle is going to be smaller than 180 degrees. Notice the major arc is going around this way, not the central angle. It's going the opposite way. And then, of course, semicircles are coming from just exactly half the circle. So we have these three types, and you need to know that they are either less than, greater than, or equal to 180 degrees. The other thing we know about the measures of these arcs is that they are, let's try that again. Is that the relationship between the central angle and its arc is that they are equal. So let me draw in some points here. Let's call this Q. Let's call this P. Let's call this point M over here. And let's say I tell you that this angle in here is 120 degrees. And then I ask you, okay, if that's 120 degrees, then what is the measure of angle PQR? What is the measure of angle arc RP? And what is the measure of arc RMP? So let's talk about this kind of in the most straightforward way. We know, I meant this to be different. That's okay. We already know the measure of PQR. PQR is the angle that you already see here. It's this angle right here. That angle we're given is 120 degrees. So then what's the relationship between the measure of this angle and the measure of its arc? Well, the thing we know is that the measure of the angle of a central angle is equal to the measure of its arc. So the arc would also be 120 degrees. So I'm going to write that down here. Central angles have the same measure as their arc. So because this is a 120 degree angle, then this arc, RP, is also 120 degrees. And then it asks, what's the measure of RMP? RMP is this arc that goes all the way around the circle this way. Well, we know the total circle is 360. So if I subtract 120 from that, I get 240. And that's how I know that RMP is equal to 240 degrees. So that's kind of the basics of what you're going to need to be doing on these lessons. So let's look at the questions in the actual lesson and see if there's any other things that we need to kind of discuss. So a lot of proofs here, so we're going to do those together. So let me jump over and let's talk through our proofs. So let's scroll down here. I've gone over all the material you see here. I've gone over. We'll talk about the arc addition postulate here in a second. We've talked about the fact that congruent central angles are congruent to their chords. So these theorems, I'll just walk us through these actually. Let's walk through these theorems. So the first one is arc addition postulate. Let's jump over here and I'll talk about the arc addition postulate. So the arc addition postulate say I have a circle made up of multiple arcs. Name all these points here. Let's call this point M. We'll call this point P, Q, R, and S. And let's say that I know that this is 92, this one is 61 degrees, and this one is 34 degrees. So let's say I knew all that information. Well, what else could I know about this? Okay. Well, let's say I was asked what the measure of arc PR is. So that's actually the arc from here all the way over to here. So PR is not actually one of the angles that I'm given. However, we know that PR is made up of arc PQ plus arc QR. And so the arc addition postulate just says that if I have the measures of the arcs that make up a larger arc, I can simply add those together and that will give me that measure for the total arc. So we know, based on what I see here, that if this is 61, then this is 61. And if this is 92, then this is 92. So this angle being 61, and since central angles are the same measure as their arc, we know that this makes 61 and this 92 makes the arc 92. And so then PR is equal to PQ, which is 92, plus QR, which is 61. And so the measure of angle PR would equal 153 degrees. And so that's how you apply the arc addition postulate. Very similar to the segment addition and angle addition postulates we've covered in the past. Let's look at these three theorems. Theorem 7.3a, in a circle or congruent circles, congruent central angles have congruent chords. In other words, if I have a circle here, and I have an angle here, and another circle here with the same measured, let's say their radius are the same, their radius are congruent, the radius of circle A is congruent to the radius of circle B. And not only that, this angle is 45 degrees and this angle is 45 degrees. Well, everything else about those are the same. In other words, the arcs are congruent to each other. That's what it says here. The chords are congruent. Those are the chords, that line I've drawn. The chords are congruent. And then the same thing is true. So if I know that the arcs are the same, then these chords are the same. So what I'm saying is that if you have two circles that are the same size and the angles are the same, then the arcs are the same. And if the angles are the same, then the chords are the same. Right? So chords, arcs, and angles always are proving one another congruent. Okay, it's pretty basic. It kind of seems a little bit obvious when you really look at it. So we will use those in some of the proofs, and I'll make sure I kind of point that out, and then I will put these examples in the notes. Okay, so let's hop down here. Okay, first things first, let's go through our proofs, and we're going to do these together. You're not responsible for doing the proofs yourself. I'm always going to go over these for you. Okay, we have given angle APB. It's this angle is congruent to angle CPD. Okay, so those angles are congruent. They want us to prove that this is congruent to this. So AB is congruent to CD. Okay, so I think we can get there. We already know there is a theorem for this, but we're going to have to prove it. So first things first, it says we have our given. Then it says AP is congruent to BP, is congruent to CP, is congruent to, okay, something about these makes them all congruent. Why is this, and should be obvious to you, this all congruent? Well, they're all radii. So AP, BP, CP, and DP, that would be answer choice E, are all congruent because they are all radii of the circle. They are all in the same circle. They are all, each one is a radius, so they all have to be congruent. Okay, well, that means that these two triangles are congruent because we just proved that we have side, angle, and since those are both have the same sides, two sides, and the angle in between, we can prove they are congruent using the SAS theorem. That's answer choice A. And then using that, since those two triangles are congruent, then we can prove that this other side is also congruent, and we've proven that right there. So we're incorporating some things from the first half of geometry. I know a lot of you weren't with us and didn't do the first half of geometry with Premiere, so that's why I'm kind of going over these for you. So hopefully that is a little bit clear to you how we're using the properties of circles to prove something about these triangles. All right, then we get to theorem 7.3d. It says this: in a circle, if a radius or diameter is perpendicular to a chord, then it bisects the chord and its arc. So if we have a radius right here, and then we have a chord coming across here, and they are perpendicular to each other, then it also cuts it in half, which means that these are congruent, and obviously the angles are congruent because they are perpendicular. But that's what that theorem 7.3d is saying, and I'm assuming the next proof is going to have us use that, so let's scroll down and look. Sure enough, it is. It says that the given is that AB is perpendicular to CD. So that's what they're showing us right here. These two are perpendicular to each other. Then it says we're going to draw a radii here and here. And that's, you can always draw, so that's why it says through any 2 points there's one line. We've drawn a line. AC is congruent to AD. We know that because they're both radii, and all radii are congruent. So we come down and we find congruent, and it says, answer choice E. All radii are congruent. Then it says AE is congruent to AE. Well, remember, we've talked about this before. Anytime we have a statement that is something congruent to itself, we're using the reflexive property. So we're going to go find that, and sure enough, there it is in answer choice F. So that's our answer choice for there. Then it says CEA and DEA are right angles. We knew that because those two lines are perpendicular. That's the definition of perpendicular lines. CEA and DEA are right triangles. Okay, well, they are right triangles because they have a right angle. So we're saying this is a right angle, this is a right angle. Therefore, ACE and CEA and DEA are right triangles. That's the definition of, and it's always going to be whatever it says here. So it's the definition of right triangles. There it is. Answer choice C. HL is a congruence theorem. So we know we're proving that two triangles are congruent. I tell you right now, it's going to be the triangles we proved from the previous one. So we should be looking for that statement that has those two triangles. All right, CEA and DEA, there it is. It's the same exact two triangles from here. So that should be obvious. That's going to be our answer, A. And then the next statement says that CE is congruent to DE. Well, where do we get that? Well, we got that from the fact that we proved these two triangles were congruent right here, this triangle and this triangle. So if they're congruent, then these have to be congruent. And that's CP, Remember, I always told you, anytime you say triangles are congruent in one statement, your next statement is always going to be CP, So that's going to be answer choice G. And actually, the rest of that is filled out for us. All right, let's keep going. Another theorem. If a circle or congruent circles, if two chords are equidistant from the center, then they are congruent. Great picture of this here. You have these two chords. They are equidistant from the circle, so therefore they have the same measure. That's pretty straightforward. All right. Again, we're going to use that in a theorem or in a proof. All right. PQ is perpendicular to AC. PR is congruent or is perpendicular to DF, and BP is congruent to EAP. So a lot of givens. All of these are given right here, and that's what you see here in number 1, given. Then it says to draw radii, AP and DP. Remember, that's going to be like the previous problem. We're going to be saying that through any 2 points, there's exactly one line. That's what allows us to draw a line. So we use answer choice A there. Anytime we draw a line and diagram ourselves, we're using the theorem that through any 2 points, there's exactly one line. So let's just cover what they actually said was given. PQ is perpendicular to AC. So let me try to get that drawn up a little better. PQ is congruent to AC, or perpendicular. PR is congruent to FD, and BP is perpendicular to EP. Okay. Then it says that AB is congruent to CB, and DE is congruent to FE. Okay, well, we know that that's because this is bisecting. So this is congruent to this, and this is congruent to this. And it says ABP and DEP are right angles. Well, we see that right there. These are right angles because we can see here that they are perpendicular lines. We said that from statement 1. So that's the definition of perpendicular lines. So perpendicular lines, there it is, answer choice K. Okay, answer choice K, definition of perpendicular lines. Then it says triangle ABP and triangle DEP are right angles. Again, that's because we have a right angle, right? So that's where we're getting that from. Let's draw that line in again. There we go. A little bit better. So that's definition of right angles, right triangles. AP is congruent to DP. Well, those are both radii. So we know that if these are both radii, then we know that these two are going to be congruent to each other. So that's because they're both radii. Let's find one. All radii are congruent. So there we go. Hop over here. All radii are congruent. What was that? Answer choice D. Triangle ABP and triangle DEP are congruent. They've given us the reason for that. Then they used CPCTC, which always follows a triangle congruence. And then AB is congruent to DE. That's just saying the definition of congruent angles. Nothing really big there. Just the fact that these are congruent means that the measures are going to be equal. So that's the definition of congruent segments. Definition of congruent. So J. Oops, yep. There we go. And that's this one. Then they did AB is equal to CV and D equals FE. That's coming from line 3. They even tell us that. Then we're using the segment addition postulate. We're simplifying that. We're working this out. All of these steps are basically us rearranging this equation until we get DE plus DE equals DF. And that's us doing substitution. That's going to be answer choice I. Substitute again from line 9, and then you're working it out. This is just simply what we call simplify, because we're simplifying this expression in 16 and we're simplifying it to be what it says in 17. So we go answer choice F, and then we're done. And that was a doozy. Do not worry about knowing how to do these proofs. They are not going to be on the test. I'm working through these because I want to make sure you're able to get through this work. So I hope you were maybe following some of that. Make sure you get these answers and pause and restart the video as you go so that you can get that. Let's keep looking though. See what else we have. All right, so now the rest of this you should be able to do. There might be another proof down at the bottom, but let's look. The measure of a blank in degrees is 360. I went over that in the notes. A blank is an arc whose endpoints lie on a diameter of a circle. I went over that in the notes. It's one of the 3 types. A blank, yeah, all of these are vocab. Either use my notes or use the vocab at the top of the screen. 8, number 9, these are all vocabulary, 11, 12, 13, all vocabulary. Okay, starting at number 14, name the part of the circle. What's the name of the circle? Name a central angle, name a minor arc, name a major arc, and name a semicircle. You should be able to do those. Notice there are 5 answer choices. The answer choices stay the same for each question. 5 answer choices, 5 questions. Don't duplicate any of your answers. Just a reminder, circles are named like you see here, or with a symbol. Oops, circle, not circle C, circle X. So that would be the name of this circle. So that would be how you do that. Minor arcs, remember, minor arcs have 2 letters, major arcs have 3 letters, semicircles have 3 letters, and they are made up of a diameter. And then central angles are just the names of angles. So you should be fine on that. That's what you do for everything through 18. So it'd be 14 through 18. And then we get to another proof. Oh, 2 proofs. Great. All right, let's go over these together. This video is going to be a little long because of all these proofs. AB is congruent to CD. That's given. So they're saying these are congruent. That's what we're doing here. AP is congruent to BP, and CP is congruent to DP. That should be obvious. That is coming from the fact that these are all radii of the circle. So they're congruent, and that's because all radii are congruent. That's answer choice E. That's answer choice E for number 2. All right, it's coming from here. Then we prove that the triangles are congruent. We know it's going to be the 2 triangles we see in this diagram. It's got to be APB and CPD. Let's see if we find those. There it is right there. Not this other one. It's got to be answer choice B. So we have answer choice B goes right here. Anytime we have congruent triangles in a statement, the next thing is always CPCTC, always. Then we have angle APB is congruent to measure of angle CPD. That's coming from 4. You can see these are almost the exact same thing. One is congruent, one is equal. That means we're doing congruent angles. The definition of congruent angles is G. So that's how we know that. Go in there. Then it says arc AB is congruent to arc CD. So now they're jumping over to the arcs. So they're saying if these angles are congruent, then these arcs must be congruent as well, which they are. come down, and that is the definition of arc measure. And then because the measures are the same, then the actual arcs are the same, and so that's congruent arcs. That's going to be answer choice F. Okay, follow along on that. Last one, thankfully, is a little bit shorter. We have arc AB is congruent to arc CD. Prove that the angles are congruent. We want to prove something about these angles, okay? Well, if the arcs are congruent, then their measures are congruent. That's just, again, the definition of the thing. So it's the definition of congruent arcs. That's going to be D. And then it says here, we're going to look for something that's the definition of arc measure. Well, we know that if the measures of the arc are the same, then the measure of the angles are the same. And so that's where we're coming in with answer choice F to say the angles measures are the same, and because their measures are the same, so are they congruent. So it's the definition of congruent angles. Answer choice E. There's a lot in there. I want you to focus on really understanding the vocabulary though, and then I will be back with lesson 4.